Today's lesson deals with Hess's law. Now we've learned previously that there's three different ways you can calculate the enthalpy change for a reaction. You can take the Q value divided by the moles, you can use bond energies, and now we've learned you can use enthalpies of formation. Our fourth way of calculating the enthalpy change is to use Hess's law. Okay, and Hess's law states that the enthalpy change during a reaction depends only on the nature of the reactants and the products and is independent of the route taken. Now what that means is it means that you can manipulate chemical equations to make them work for what they're asking you about. Okay, so to use Hess's law, what you do is you write the chemical equation for the required enthalpy change. So they're going to give you an equation. They're going to say, what's the enthalpy change for this reaction? And then you're going to use some equations before that to basically, remember with reaction mechanisms where we would add 1, 2, and 3 equations together to get the overall equation? That's what we're going to have to do here, but here you're going to be able to manipulate those equations to do that. Okay, so to manipulate equations, what you can do is you can flip them. So if you're doing a chemical reaction and you have to have CO2 as a product, and in one of your reactions it's a reactant, well, we're going to flip that equation. And when you do that, it reverses the sign of the enthalpy change. Okay, let's say you need 2 CO2s instead of 1 CO2. Well, then you can multiply them by whatever number you need to, and when you do that, that multiplies the enthalpy change. And then, of course, just like with reaction mechanisms, you can add equations together, and when you do, you add the enthalpy changes together as well. Okay, so those are really the three main things you're going to do with chemical equations. Sometimes you'll flip them, sometimes you'll have to multiply them by 2 or maybe multiply them by 1/2. Okay, but what we're going to, and really we can just do some examples, and that's really going to help you understand Hess's law. So example 1 says, calculate the standard enthalpy of formation of ethane given the following combustion data. Now what they don't do here is they don't give you any equations at all. They want you to come up with the equations. So this is a good practice for us. So the enthalpy of formation of ethane means we have to create ethane, remember, from its elements. So we know that we're going to have 2 carbons plus 3 H2s is going to make C2H6. And they want to know what's the enthalpy change for that reaction. And they're giving us the following combustion data, which means that when you react those things with oxygen, you're going to get some type of product. So we got to figure out those equations as well. When you combust carbon with oxygen, you get CO2, and they tell us that the enthalpy change for that reaction is -393. Okay, when you combust hydrogen, you get just H2O, and the enthalpy change for that is -286. And they tell us that the combustion of ethane, C2H6 plus O2 makes CO2 and H2O. And that delta H is -1560. Now obviously these equations need to be balanced. The top one already is. The bottom one, it looks like, needs some couple of 2's right there. And I think on this one we're going to end up having to double everything. So 2 times 6 is 12, that makes 6, 8 plus 6 is 14, 7. Okay, and so now here's our job. Our job now is to take these 3 equations here and again try to create them in such a way that when we add the 3 of them together, all we get is this top equation up here. That's what Hess's law is. So for example, we need 2 carbons and we need them to be reactants. Well, down below in our first equation here, we have 1 carbon. It is a reactant, which is good, but that also means that we need to therefore take this whole equation here and we need to double everything. 2, 2, and 2, and that also means we have to double our enthalpy value. 393 times 2, I believe, is -786. Okay, and that's our value now that we're going to use. Okay, and then we need 3 hydrogen molecules, again, as a reactant. And we have 2 right here. We need 3. So again, we're going to multiply this whole thing by 1.5. So that's going to make 3 here. 1.5 times 1 is 1.5 O2s. And that makes, excuse me there, instead of 2 H2Os, 3 H2Os. And now I got to take 286 and also times it by 1.5. So I believe 286 times 1.5 is negative 429. Actually, I'm not sure. Let me make sure. 286 times 1.5. Yeah, 429. Okay. Okay. And then for our last equation, or for our last part, we need C2H6, but we need it to be a product, and we only need one of them. Well, here you can see we have C2H6, but it is a reactant, and there's 2 of them. So not only do we have to flip that whole equation, we also have to cut that whole equation in half. So when we do that, I'm gonna cut it in half and flip it, and then I'll erase this whole top one. So when we flip it, that means we got to make our products the reactants. And I'm going to cut it in half. So that's going to go back to 2 CO2s plus 3 H2Os makes C2H6 plus half of 7 is 3 halves, or excuse me, 3 1/2, so 7 halves O2. Now, when you flip an equation, it makes the sign positive, and we're cutting it in half. So delta H is positive 1560 cut in half, which I believe is positive 780. So now this whole equation here is gone because we flipped it and we cut it in half. Now, if we've done this correctly, everything will cancel except the part that they're asking about. We should only have 2 carbons left, 3 hydrogens, and the C2H6. Now let's see if that's correct. Now, if things are the same on both sides, we're going to cancel them out. And what I mean by that is you can combine them together. For example, on the reactant side here, in those 2 reactions altogether, there's 2 oxygens plus 1.5. That makes 3.5 oxygens. Well, over here on the product side, we also have 3.5 oxygens. So those and those cancel. Okay, and then down here we have 3 waters on the reactant side. Up here we have 3 waters on the product side. Cancel. And then in the first reaction we have 2 CO2s. In the last reaction on the reactant side we have 2 CO2s. Those cancel. So again, if you have the same thing on the reactant side and on the product side, they cancel. And you'll notice that overall, 2 carbons, 3 hydrogens, and our C2H6 are all that we have left. So now that we know that our equations are correct, we hope that we did our math correct. So now I can take my negative 786 minus 429 plus 780, and I get, once I add this and this and this all together, my final enthalpy change for that reaction is negative 435 kilojoules per mole. Check my math, make sure I did that correctly. I might not have. Okay, let's go to example number 2. Example number 2, the thermite reaction was used to produce molten iron for welding railway tracks together in an extremely exothermic process. Part A, calculate the enthalpy change in the thermite reaction given the standard enthalpies of formation of iron 3 oxide and aluminum oxide respectively. Okay, so they want the enthalpy change for that reaction, and they're giving us enthalpies of formation. Okay, enthalpies of formation makes me think, okay, the enthalpy change for the reaction is equal to the enthalpy of formation of the products minus the enthalpy of formation of the reactants. And in this case, elemental form, so those both have enthalpies of formation of 0, and that's our answer to B. Why are no values given for the enthalpy of formation of aluminum or iron? Simply because they're in their elemental form and they do not have enthalpies of formation. So the enthalpy change for the reaction is enthalpy of formation of the products. Al2O3 is aluminum oxide, so that is negative 1675, minus the enthalpy of formation of the reactants. The reactant is iron 3 oxide, which is negative 823. Again, notice that double negative there. Do that correctly. Negative 1675 minus a negative 823 gives me a value. The enthalpy change for that reaction is negative 852 kilojoules per mole. Okay, and then part C, what would be the enthalpy change to convert 1 mole of aluminum oxide to 2 moles of aluminum using iron as the other reactant? So basically, this is the only part that deals with Hess's law. A is not Hess's law, B is not Hess's law, but C is saying what would be the enthalpy change to convert a mole of aluminum oxide? So again, let's come back to our balanced equation here. We're going to convert this to aluminum using the iron as the other reactant. So basically they're saying, what if we flip that equation? If we flip that equation, what would the enthalpy change be? Well, we know that if you flip the equation, you just flip the sign of the enthalpy change. So it would just be 852 kilojoules per mole, and obviously that's a positive value rather than a negative value. Okay, example number 3 here. Hydrogen gas burns in air according to the equation below. You've got H2 plus O2 making H2O. Calculate the standard enthalpy change, so the enthalpy change at 298 for the reaction represented by the equation above, and again they give you enthalpies of formation. Remember, enthalpy of formation of hydrogen is 0, oxygen is 0 because they're both in their elemental form. So again, the enthalpy change for the reaction is the enthalpy of formation of the products, which we do have an enthalpy of formation of, 2 times negative 285.8, minus the enthalpy of formation of the reactants, which are both 0. So the enthalpy change for that reaction is equal to 2 times negative 285.8, which is negative 571.6 kilojoules per mole. Okay, and that is all you have to do on part A. Okay, part B, calculate the amount of heat in kilojoules that's released when 10 grams of H2 is burned in air. Okay, and so this is where, again, we're still not to the Hess's law part. This is just obviously enthalpies of formation. This is now we're using Q here. So 10 grams of H2, so 10.0 grams of H2. Remember, calculate the amount of heat means the Q value, which means you're going to use that enthalpy change to get rid of that. Okay, and we know the molar mass of hydrogen is 2, so there's 2 grams in 1 mole of H2. And remember, this 571.6 is per mole of reaction, so we need to say 2 moles of H2 from that balanced equation is in 1 mole of reaction, and then 1 mole of reaction. And again, here they're saying that is released, which means you don't need to put the negative in, 571.6 kilojoules. So 10 divided by 2 times 571.6 equals 1,429 kilojoules is the amount of heat released. So we're going grams to moles, and then going from moles of the reactant to moles of the reaction, and then going from moles of reaction to the kilojoules. Okay, letter C. So finally here we're getting to the, again, the Hess's law component. Given that the molar enthalpy of vaporization for H2O, so vaporization is what? Converting a liquid to a gas. So we're going from H2O liquid to H2O gas. They say that the enthalpy change is 44.0 kilojoules per mole. Okay, it says, what is the standard enthalpy change for the reaction two H2 gases plus O2 gas makes two H2 gases. So up here, that was to H2O liquid. So now they're saying, okay, instead of liquid, we want you to go to gas. So we need to take this top equation up here, which we know the enthalpy change for that reaction is negative 571.6 kilojoules per mole. And again, we have to take this equation and we're going to add it to this equation right here to make it have gas at the end rather than liquid. The only difference is we need, obviously up here, there are two waters that are liquids. And down here in our overall equation, there's two waters that are gases. So what do we need to do to this equation? We need to double it. So 2 and 2, that makes that 44 become 88. And now look at our two H2O liquids. We've got those as reactants. Here we have them as products. They are going to completely cancel out, leaving us just with H2O gas. And so we can take our negative 571.6, and again, it's the enthalpy, or we're not using enthalpies of formation here. Sorry, we're using Hess's law. We're going to take this, and remember, you take this equation, you add it to the other equation, so it's negative 571.6, and we're going to add plus 88. And so to get it to a gas rather than a liquid, it only releases 483.6 kilojoules per mole instead of the negative 571.6. Okay, and it says what's the enthalpy change? So yes, we do need that negative in there. So the delta H, but when we add those two equations together, it gets us to negative 483.6. Okay, so that is now our fourth way of calculating to find the enthalpy change for a reaction. There is one more that we'll learn about tomorrow. But there's our Q value, and then taking it, dividing by the moles, using bond energies. This is just a good summary of everything we've learned so far. Using enthalpies of formation of the products minus the enthalpies of formation of the reactants, and then again what we just did, manipulating equations and using Hess's law to find that value. Okay, and remember, our last thing here is just don't let bond energies confuse you with intermolecular forces. Okay, the energy in a bond, remember, is how much energy it takes to actually break that bond. Okay, but remember from Unit 3 that when you're talking about intermolecular forces, what you're doing is when you're going from a solid to a liquid or a liquid to a gas, those are physical changes. It's still water. You're breaking the attraction between molecules. Okay, if there's a rearrangement of the intra-bonds, the intramolecular attractions, then it's a chemical change. Okay, when salt is dissolved in water, again, remember, we can think of that as three different events. There's it's endothermic. The NaCl is breaking apart, so what's being broken, you're actually breaking the attraction, the intra-bond between the sodium and the chloride ions. Okay, and then the water separates from each other. Okay, and in that case, that again, it's just water separating, and so that is an intermolecular attraction that's being broken. And then the third event is the sodium and the chloride ions. And remember, those first two, the first and the second, those are both endothermic. And then the third event is the individual sodium and chloride ions being surrounded by water molecules. Okay, and again, that is absolutely an exothermic process. Okay, what is it about water that allows that that allows that even to occur? And what are the attractions? Those are called, we know those are called ion dipole forces that exist between the sodium ion or the chloride ions and the polar water molecules. Okay, and that's a good introduction there to Hess's law.